Like I was. So I didn't sit
All right. It is time to get us started. Thanks for joining us today for this lecture and the annual lecture series at the Center for Philosophy of Science. It's my great pleasure to introduce Melanie Mitchell, who's professor at the Santa Fe Institute. Melanie got her PhD with Doug Hofstadter, and as I was commenting, her PhD was about copycat. If any of you has worked on analogy, copycat has a sort of a mythical status in cognitive science. And I was actually very impressed to be able to meet the author of Copycat, which is really a classic piece of work in cognitive science. I'm extremely impressed. So, some of you will not know her for her work on Copycat, but more for her work on complexity, because she was also one of the leading thinkers of research on complexity, in particular with her book, Complexity, a Guided Tour, published with OUP in 2009. The book won the 2010 Phi Beta Kappa Science Book Award. As others, I will not know her for her work, neither on Copycat or on complexity, but for her more recent work on AI. And she's been one of the leading thinkers in the last 5-7 years, maybe 10, on how AI is developing and what to make of it. If you read Science, which I hope you do on an occasional basis, you must have met her because she's a very regular contributor of pieces to Science about how to understand some development in AI. I will mention her 2019 book on the topic, Artificial Intelligence, A Guide for Thinking Humans. I guess that's you. And that book won many awards and prizes. It was shortlisted for the 2023 Cosmos Prize for Scientific Writing. Melanie won many prizes. I will just mention one, which has a connection with Pittsburgh, the Herbert A. Simon, that's a connection, award of the International Conference on Complex Systems. And she won also many other prizes. We're extremely pleased and honored to be able to host her at the center today. So thanks for, I know you're extremely busy, so thanks for coming and joining us. Floor is yours.
Thank you. Thanks everybody for coming. I'm excited to be here. So I'm going to be talking about AI's challenge of understanding the world. And this is, as Edward mentioned, I have a regular column that I write in Science Magazine, and one of the columns was about this challenge. So this talk is really quite an expanded version of that. So do AI systems understand the data that they process about the world? And does it matter? Do we care if they understand? Understand is one of those words that can mean many things, and many people have different opinions about it. But it does seem like in the past, at least, AI has had some failures of understanding, if you just try and take the word in its colloquial sense. So this is a paper that came out in 2018, sort of the dark ages of AI, pre-ChatGPT. And you know that back then, deep neural networks were very big in computer vision. They were able to do very well on object recognition and images. This is a deep neural network is able to recognize this school bus as a school bus with 100% confidence. But these researchers showed that understanding of the notion of school bus was to that network somewhat brittle, because if you changed something about the image, like the pose of the object, it's now 99% confident it's a garbage truck. Or here, 100% confident it's a punching bag. Or 92% confident it's a snowplow. And it was not hard to sort of break these systems to find cracks in their understanding of the data that they were processing. This was shown in the real world in many ways. I liked this little example of someone who was tweeting. He was driving his Tesla using self-driving software, and he said that his car kept slamming on the brakes in this area with no stop sign. But after a few drives, he noticed that billboard, which I don't know if you can see. There's an official like police officer or something holding up a stop sign in an ad for something. And the car said, oh, stop sign, better stop. So this is a failure of understanding what he called an edge case of the real world, the kind of thing that doesn't happen that often, but humans certainly know how to deal with this kind of thing. And then this whole idea has been adopted by, say, people in San Francisco who are now trying to fool robo-taxis driving around San Francisco by wearing stop signs on t-shirts and show that it actually works. Other kinds of failures of misunderstanding have been common in machine learning. Here's a paper where researchers were using deep neural networks to classify pathology images as either malignant lesions of the skin or not. And they trained on a lot of different images from data sets of skin lesions, and their neural network did very well. But when they just looked more deeply into what it was doing, here's what they found. They noted that the algorithm appeared more likely to interpret images with rulers as malignant. And you can see that, when a pathologist is analyzing a skin malignancy, they want to measure the size of it and so on. So they put a ruler. And so this was a spurious correlation that the network picked up very easily and was using it to classify images and happened to do very well. But of course, this in machine learning is called a shortcut, that's based on some aspect of the data that's not part of what the goal of teaching the network is. And here, the neural network did lack the understanding of what it was supposed to be learning. Other examples in translation, Google Translate still has some problems with words. And if you speak French, you might see the problem here. I gave it this sentence about a legislator accidentally leaving a copy of the bill he was writing in the taxi. The word bill, of course, can mean different things, and it's translated into French as the kind of bill that an invoice, something a plumber might give you, not a legislative bill. And these kinds of translation mistakes, not that one, but other ones can actually have serious consequences in the real world, such as when they're used to translate asylum cases from Afghanistan and were found to create errors that really did have effects like that. But now we're in the age of generative AI. We have large language models that have been claimed to have a much richer understanding of the world than these previous systems. And in fact, I could ask ChatGPT, right, to translate the same sentence into French, and it has the correct translation of that term. And I can ask it why, how did it know? And it could tell me at great verbosity, why it's doing it and all the different things that it might have done instead and so on. But it does really seem to have a more deep understanding of the world. Terry Sinofsky, who's a neuroscientist and also one of the pioneers of neural networks and connectionism, wrote about large language models and said that it's sort of like a space alien suddenly appeared that could understand us, and it says some aspects of their behavior appear to be intelligent, but what is the nature of their intelligence? And that's something that we're all grappling with, right? Probably many of you here are still grappling with what is the nature of the intelligence of these systems? How can we characterize it? How do we think about it? Well, people have very different opinions, of course. Blaise Aguirre-Iarcus, who's a researcher and vice president at Google, wrote this paper about how large language models do, in a very real sense, understand a wide range of concepts, understand language, even though their understanding is purely informed by text. Whereas Jake Browning, who's a philosopher at NYU, and Jan LeCun, head of AI at Meta, have the opposite view. They say a system trained on language alone will never approximate human intelligence, even if trained from now until the heat death of the universe. So really differing views in AI. This is, people have maybe even more than I've ever seen in the field have diametrically opposing opinions about this. So we might ask, how can we evaluate understanding in large language models? And there's many different ways that people have been trying to do it. One is just to look at their behavior, give them a kind of a Turing test. Do they seem like they understand? And yes, they do. I showed you the example from translation, and many of you have interacted with these systems, and they give you a very strong sense of understanding. But of course, that's subject to what's been called the ELIZA effect, which is our human tendency to project understanding onto anything that communicates with us in natural language, like the really dumb chatbot ELIZA back in the 1960s, which people really felt understood them at some level. Okay, so a more objective way to assess understanding is to test them on benchmarks that were designed to test different kinds of understanding. And in fact, they've done quite well on such benchmarks. This was in Nature a few months ago, saying that AI is now beating humans at basic tasks. And some of the benchmarks that they're doing well on, this picture shows the human baseline, sort of how humans do on a given benchmark, and for each benchmark, where we are, where AI systems have gone over the years. And you can see they're exceeding humans on benchmarks like visual common sense, natural language inference, reading comprehension, multitask language understanding, et cetera, et cetera. So does that mean that AI systems are now better than humans at visual common sense, at reading comprehension, at language understanding? Well, of course not, because even though the benchmarks have these names, it doesn't necessarily mean that they test the underlying general ability that they're named after. There's a phrase that was used by the AI researcher Drew McDermott way back in the 1970s. He called this kind of naming wishful mnemonics. And what that means is that, if you name something that, reading comprehension, then maybe it will actually be reading comprehension, but so still wishful. So the problem, of course, is that for many of these benchmarks, we don't know how much of them or very similar things are contained in the training data of these systems, whether they're using the kinds of shortcuts that in language that are equivalent to the ruler shortcut that I showed you before, or are they using what some people have called approximate retrieval, that is retrieving examples from the training data that are similar to the kinds of questions that they're being asked, rather than doing a more general kind of reasoning or understanding. So those are possibilities. And many people in AI have said that AI evaluation is broken because we have these benchmarks, but we don't know what they imply about real world behavior or success. Another way that people are looking at the understanding of AI systems is to probe them for what's called emergent world models. So world model is kind of a notion that we humans might have these models in our heads about the world that we can use to simulate or predict or reason about things. And maybe AI models have developed them too. So Ilya Sutskever, who was one of the co-founders of OpenAI, proposed that this was the case, that he said that when we train large language models to predict the next word in lots of different texts, what they learn is a world model, a projection of the world, and he goes on and on about humans and their hopes and dreams, etc. The neural network learns a compressed, abstract, usable representation of that. Okay, so that's a little vague, but he's saying that there's some kind of something more than just associations in there, you know, co-occurrence statistics, whatever. There's actual usable models of the world that these things have somehow grasped just by predicting the next word in lots and lots of text. So what's the evidence for such world models emerging? Well, it's hard, of course, to analyze these giant, you know, trillion parameter models, but people have tried to find evidence for the ability to learn world models in simpler systems. So this was a paper that talks about the emergence of world models in a game playing program, just from training on sequences. They look at a game called Othello. Maybe some of you have seen this work. Othello is a simple 8x8 board, 2-player game where, how many people here know can play Othello? Have seen it? Okay, not everybody. So it starts out with this configuration of black and white tiles on the board, and black moves next, and black can only move to squares where if it puts down the black piece, it'll have a black pieces surrounding a white piece. So for example, here, the black moved at square E3, and that surrounded the white tile, so the white tile flipped to black. Okay, and now white can move. Here, white moves to D3, and the black tile in the middle flips to white. And so they keep doing that until can't move anymore, and whoever has the most tiles wins. So what this group did was they trained a transformer network, sort of like the GPT models, except much simpler. This one only had 8 layers as opposed to hundreds of layers. And they trained it on sequences of games. So a game consists of a sequence of moves where, you know, each coordinate here, all you need to know is, you know, D4, C4, et cetera. You could list the game in terms of that sequence where each token is a position. We know black always goes first. So what they did is they generated 20 million games using a game generator, and trained this model to predict the next move, the next token in the sequence, from taking each possible sequence in each of those 20 million games. And the network got very good at predicting the next token. It didn't know anything about the game. It wasn't told it was playing a game. It wasn't told it was a 2-person game. All it had was the sequence of tokens, just like, you know, ChatGPT just is trained on sequences of language tokens. This was trained on sequences of game tokens, game move tokens. And it learned to do that prediction task very well. And what they did, the researchers showed that the intermediate layers in the network could be simply decoded using a linear classifier to predict the state of the board at any time during a sequence. So basically, they feed in a partial sequence, and then they take the activations in the intermediate layers, and they train a classifier, simple linear classifier, to predict for each of the squares, is there a black or a white or an empty square there? And what they concluded, that because they could do that, they concluded that Othello GPT had learned an emergent world model of the Othello board, of the game, of the dynamics of the game. And they showed that by changing activations, that the actual representation was causally relevant for the performance of this model on predicting tokens. Okay, so people got really excited about this result. Chris Olah, who's one of the founders of Anthropic, said that this is a clear evidence of a language model developing an internal world model. Andrew Ng, who's a famous guy in machine learning, was the founder of Google Brain team, said, do large language models really understand the world or just give the appearance of understanding? Evidence from Othello GPT shows they build models of how the world works, which makes me comfortable in saying they do understand. This is sort of the notion of understanding that these people were talking about. But the problem is, if you actually look very deeply into what the Othello GPT model had learned, and some people did after all of this, they found that what it had learned was what they called a bag of heuristics. It wasn't like some very neat, elegant model of the board that you can sort of generalize. It was really a whole bunch of very specific rules about if the sequence looks a certain way, then the configuration is going to look this way. If the sequence looks a certain way, it's going to look this way. So it's a little bit debatable whether this really should count as a world model, since it is very specific to these very specific heuristics or rules and not generalizable in any way. Okay, so world models is still a big thing for a lot of people studying these systems, and people are debating what that means and how to probe for them better. But other people are saying, okay, well, let's evaluate these systems on tasks that require abstraction and reasoning, since those are strong sort of correlates of what we think of as understanding. So there's been a lot of buzz lately on the notion of reasoning in these systems. You know, OpenAI just came out with their so-called O1 model, which is specifically trained to do reasoning. And many people have made many claims about reasoning in these models. But then there's been some more critical research, like this paper, which is called Reasoning or Reciting, exploring the capabilities and limitations through counterfactual tasks. And what this paper did was say, okay, here's several domains for testing the capabilities and sometimes reasoning capabilities of large language models. They took, and GPT-4 did very well on these. Those are the blue bars of accuracy. But they said, what if you take the specific tasks, and you change them so that the same kind of reasoning is involved, but the content is less likely to be similar to the training data. So let me give you an example of that. So let's look at code execution. So GPT-4 is good at taking a little snippet of Python code and saying what it does, printing out the result. And so here's how they say, you know, you're an expert programmer. What does the following code snippet in Python print? You always have to give them a little pep talk before getting them to do anything. Tell them they're a genius. You know. So what they did for the counterfactual version of this is say, pretend there's a counterfactual version of Python in which lists and arrays and so on are not indexed at 0, but rather indexed at 1. Now, what does the code snippet print out? And they didn't test humans programmers, but I think human programmers would be able to do this. I'm guessing. I don't know. You can tell me whether or not you think so. But GPT-4, that's the red bar on this counterfactual task, did much, much worse. Because in principle, possibly because it had been trained on tons of Python code and was very much relying on its knowledge of how Python worked and could not adapt that knowledge to a very, very similar but slightly tweaked version. Okay, and what the authors said is that while large language models may possess abstract task solving skills to a degree. They often also rely on narrow, non-transferable procedures for task solving. So they are better at tasks that are much more similar to what they've seen in their training data. And this is a sort of a failure of abstraction in some ways, or generalization. And this same conclusion has been reinforced by many papers. This paper, which was called Embers of Autoregression. Anybody see the paper called Sparks of AGI? This title is kind of a play on that. I thought it was kind of clever. And what they showed was that for many different tasks, kinds of like puzzles, especially, but other tasks, that if you test GPT-4 and some other models on the version of the task that's likely to be common in the training data, it does much better than a version of the task that requires the same abstract reasoning, but is much rarer. Another recent paper on this that came out recently from a group at Apple showed something similar. They showed performance on a particular set of math word problems goes way down. This is the amount it decreases for each of these models. If you add in slightly, well, a little bit of irrelevant information. I don't know how humans would do on this one either. I think this might mess some humans up as well, but I'm not sure. And our own work, my work with my collaborator, Martha Lewis, on this looked at some claims about emergent analogical reasoning. So this was a group at UCLA who made claims about GPT-3 and GPT-4 and its emergent ability to do zero-shot analogical reasoning. And this got a lot of press. Undergrads get beaten on questions like those that help them get into college. Okay. So they looked at several domains for analogical reasoning. They looked at the letter string domain, which is what we did in this copycat project that Edward mentioned. And these look like this. These analogy problems look like this. You have a string of letters that transforms into another string of letters. Now do the same transformation on a new string of letters, okay? And there's no single correct answer. There's many possible answers, but people usually agree on what is the best answer. They would say I, J, K, M, sort of going to the next letter in the alphabet. And there's many different variations on these problems. You can give little patterns like here you have a double B and here you only have a single B. Here you have an almost correct sequence and here's the correct sequence, and do the same thing here. There are many variations. So the other thing that this group looked at, another domain they looked at was what they call digit matrix problems, which are matrices that have some pattern either down the rows or across the rows. Here the pattern's pretty simple. Here the pattern is the digits are permuted in various ways. Here the pattern is that you take the first two in a row and take the union of those and make that into the third. And there's other ones as well. And these were meant to be inspired by what are called Raven's progressive matrix problems, which are used in IQ test, if you've ever seen those. And what they showed is that for letter string analogies and digit matrix problems, GPT-3 was on average better than humans, okay? In some cases by a lot. And so the claim was that these systems have emergent properties, emergent capabilities for analogical reasoning. So what my colleague Martha Lewis and I did was we tried to evaluate the robustness of these claims by doing this kind of test with variations on these problems that are less likely to be similar to the training data. And the way we did for letter strings, we looked at two different variations, one of which you use a fictional alphabet in this case, one where two letters were swapped, E and M. And then you have to do the problems in the world of the fictional alphabet, okay? Or here's another alphabet of symbols. Rather, you replace letters by symbols rather than having letters, and you give problems in the world of the fictional symbol alphabet, and the problems are just the same kind of problems. And we found that for people, we did experiments on humans on prolific website for crowdsourced experiments. Human performance didn't change all that much as you varied the number of letters permuted or used symbol alphabets, but the GPT models tended to do much worse than they did for the original. And for digit matrix problems, we just looked at a very simple variation in which the position of the blank where you put the answer is changed. So instead of always down at the bottom right, you put it in a random position. And here we found that humans didn't, here's where the random position, their accuracy was, more or less the same, whereas the GPT models went way down in accuracy. They couldn't adapt to that very simple variation. But, we had shown that they actually understood that there was a blank there, because we asked it separately questions about what's the position where you should give the answer, and it was totally perfect at that. But it couldn't, for some reason, it couldn't solve the problem that way. So here's the question, Jan LeCun, who's a critic of large language models, asks, do they perform reasoning or approximate retrieval? And his opinion is there's a continuum between the two, and large language models are mainly on the retrieval side. Other people very much disagree. Yesterday, I went to a talk over at CMU by Noam Brown from OpenAI. I don't know if anyone here went to that, but he was very much saying now they can do reasoning much better than most people. So there's, again, debate about what they're doing exactly. But the take-home message is that they're much better on solving reasoning tasks that are similar to those seen in the training data, which reflects some failure of abstract understanding. Of course, people also are better at reasoning on familiar content, but it seems, at least in our results, that people were able to overcome that bias maybe through having some metacognitive ability to realize, sort of to take what they know about a particular domain and apply it to a novel domain. So how do we get humans to do that kind of thing? Well, one of the things that cognitive psychologists talk about quite a bit is the notion of concepts and their flexibility. Now, concepts is another one of those terms that's very, means a lot of different things. It's not clear exactly what people mean when they say concepts, but one way to think about it is these mental models of categories, situations, events, and one's own self and internal state. So if you want to think about these sort of world models, if you will. So consider a simple spatial concept like something being on top of something else. Okay, well, we know a lot of things about concepts. Some of their properties, that they have compositionality, is very important. They, if you understand one thing being on top of another thing, you can understand other things being on top of that. They have systematic properties, such as if you understand a cat on top of a television, you will understand a television on top of a cat. I got this image, the cat on top of the television, to be drawn by DALL-E. That was easy, but to get it to draw television on top of a cat was much harder. It's less common in its training data, but humans don't seem to have so much of that problem. Concepts also have causal structure and enable us to have predictions, reasoning, and common sense. So for example, kids, when they're very young, by playing around in the world, they can figure out what happens when you do things to things that are on top of other things. They can figure out how to get their own bodies on top of things, something that every parent has to deal with at some point. And they can figure out topological properties, like if your shoes go on top of your socks, then you have to put your socks on first. Some kids have problems with that. And of course, you know, when you get older, you start being able to abstract concepts to new situations metaphorically. And here's a bunch of things I thought of that we use the notion of on top of in a metaphorical sense, such as the top of a social hierarchy. You know, we tend to map space into other non-spatial domains. The psychologist Larry Barsalou defined a concept. This is not a standard definition, but he defined it as a competence or disposition for generating infinite conceptualizations of a category. So he's envisioning it as a generative model in which you can take something like on top of and just generate infinite conceptualizations of it. And I think I like that definition. I think it makes sense. Lakoff et al., of course, I'm sure many of you are familiar with his work on metaphor, where his idea is that any abstract concept we have is actually grounded in metaphors involving typically physical concepts, such as, you know, she gave me a warm greeting, where we're mapping temperature to social interactions, or she's 2 rungs above me on the corporate ladder, you know, status to physical location. And Liz Spelke, who is a developmental psychologist, has proposed that all concepts are grounded in what she calls core knowledge systems. And those include things like the world is made up of objects, and objects have certain properties and they interact in certain ways. We know simple things about numerosity. People understand very early on what greater than and less than means, or something being bigger or smaller, and other kinds of basic things about space and time, and also about agents and goal-directed behavior versus non-agents who aren't driven by goals. So all that's just how some cognitive psychologists have been thinking about human concepts. And some of these things seem to be lacking in these AI systems. And it's been proposed that trying to build in more of this into AI systems will make them be able to abstract and be more robust. Recently, the work of Francois Chollet from Google has gotten a lot of attention. He wrote this interesting paper called On the Measure of Intelligence, and created what he calls the ARC, or abstraction and reasoning corpus, which is a set of puzzles that are meant to test either a human or a machine's ability to do this kind of abstraction in a few-shot way that is inspired by core knowledge systems. So here's one of the puzzles in the ARC domain. Okay, so the idea is that you have a small number of demonstrations, 2, 3, 4, no more than that. And the demonstrations show how one grid transforms into another grid. So these are like 2-dimensional concept induction problems, pattern induction problems. And I think most people sort of immediately see what's going on in this and can do the same thing to a test input. So you're really good at this few-shot concept induction, or, you know, rule induction. Okay, here's another one for you. This one's a little bit trickier. Tell me if anybody sees the rule here. Yeah? Yeah, so the rule is it's basically a shape invariance task where different kinds of shapes are colored different colors, even if they're rotated or scaled in different sizes and so on. So Chollet created 1,000 of these tasks, published 800 of them. He kept 200 of them as a hidden or private test set. And he put them on the Kaggle website, which is a platform for machine learning challenges, offered some money, $20,000 for teams to compete on this, on the private, they submit their they build a program, they submit it. They can learn on the published problems, but there's only 800 of them, so it's not like a lot, say for a neural net. And then they're tested on the private test set. The best program, this was 2020, over 900 teams ended up competing, and the winning program got about 20% accuracy. Human accuracy hasn't, the test set is private, so no, it's hard to test humans on it, but people have estimated about, 70 to 85% for humans, the average human, and maybe 100% for, humans who are really smart or try really hard. Okay, let me just go on here. Now there's a bigger prize, $600,000 for it. So somebody decided that they really loved this challenge and wanted to get people interested in it, and offered $600,000 prize for a program that exceeds 85%, which is sort of the high end of average human performance. And so you can enter this now and you can vie for this prize. Right now, the leaderboard, the highest scoring program is about 55% accuracy. So there's still quite a gap, but it's getting better. But the way this works is a very, to me, unsatisfying brute force approach. And I can tell you about it if you're interested. Okay, so let me just say one more thing about ARC. One of the problems with this set, I really like this challenge. I think it's kind of brings out a lot of issues about human abstraction and in general in this very idealized form. But a lot of these problems are pretty hard even for people. There's that 15% that hardly anyone ever gets. But also they don't systematically test understanding of concepts. So I showed you that shape invariance problem. So if a computer program solves that, does that mean that it sort of grasps the notion of shape invariance? Well, we don't know, because there could be some shortcuts. This is the problem. And I think that, when people in CogSci are testing, say, children for understanding, they test them on many variations of the same problem to make sure that they're really getting it and not using some kind of shortcut. So what my collaborators, some of my collaborators at Santa Fe Institute and I did was we created a set of new problems in this domain, what we called concept ARC. And what it is a set of, we have this set of concepts. We had 16 concepts that we came up with that are very simple semantic and spatial concepts like center, inside versus outside, etc. And we created many, many variations. For each of those concepts, we created 30 different tasks that instantiate that concept. And I'll show you an example here. And we tried to make them as easy, pretty easy for humans at least. Okay. So this one, probably seems obvious to most people. Delete the bottom object. And we tested people on this, and we tested the program that won that Kaggle competition, and we tested GPT-4 in two ways. One, giving it just a text version of the arrays with colors encoded as numbers, and one in which we actually gave it the actual images. Okay. Here's another version of the same concept. Before it was remove the bottom object. Now it's color the top row red. So top, bottom, etc. Everybody got that right? Here's another one on the same concept. Remove the top and bottom objects. humans, no problem, but the programs got that one wrong. And more generally, if we look at across all of the different concepts we looked at, and each of these rows represents the accuracy over 30 different tasks in that concept group, you can see that overall people are scoring pretty highly. This prolific, people on prolific is kind of a noisy measure. Some of them aren't really trying hard. Some of them are using GPT or chat GPT to solve the problem. But overall, they did pretty well. And you can see the other programs, especially the vision program, is very bad. But the GPT-4 also not great, at least the way we were prompting it. The Kaggle first place program is now getting 50% instead of 20% because our problems are so much easier. There's still a big gap with humans. So to conclude, I started out with the question, can AI understand the world? And I think yes, in principle. There's no in principle reason why not. Current AI can do some amazing things, but it still has some failures of understanding, which makes it unreliable for many applications. And perhaps what we really need, if we want these systems to understand the world in a human-like way, we may need them to understand these core knowledge systems and the resulting concepts, which have these kinds of attributes of concepts I mentioned before. And then there's always this big question, which is, can you get AI systems to understand the world without some kind of embodiment or active intervention or interaction in the real world? And this is an eternal question in AI and cognitive science that I don't think, it's kind of going to be an empirical question ultimately, what the answer is. Okay, I'll stop there and happy to.
I've got plenty of time for questions. I raise my hand. Go for it.
I'm calling for the talk. So your talk is suggesting that AI systems lack understanding that humans do. That's why they have trouble predicting novel instances or solving novel problems. And so your solution seems to be to impose some sort of concepts, but that seems to be going against what a lot of AI community endorses as what Richard Sutton calls the bitter lesson, that essentially in order to, there's, can interpret the scaling law in many ways, but essentially like the more compute, better problem solving. Which in the cognitive science community is also sort of like appropriated in a general domain specific way. I'm like very fascinated to think like, very fascinated by this talk because it seems to me to like be going against a lot of what seems to be like mainstream thinking in this area.
Yeah.
And so do you disagree with the bitter lesson?
Yeah, that's a great question. So, machine learning, it's the sort of philosophy of machine learning says, make your system as unbiased as possible, learn from the data. When it's there, the data will give you everything you need. Bitter lesson saying, don't put in any sort of structure or biases or prior knowledge, whatever, because then you'll bias the system and you don't know, that means you'll limit it. And that's worked very well, except for the fact that you need so much training data and so much energy, and big companies like Microsoft are buying their own nuclear power plants to, power their systems. And so it seems like there's something wrong there to me, at least if you have to do that. You don't have to buy a nuclear power plant necessarily to power your child. Maybe, I don't know. But humans are biased. We have a lot of biases, but we're much more data efficient in many ways. We learn from, we can do things with just a few examples. And that just seems like that, there's always that trade-off between flexibility, ultimate flexibility and efficiency. But I think maybe machine learning has gone too far in the bitter lesson direction and needs to come back a little bit because it does lack some of the important features of human learning, which is efficiency and robustness.
Yeah, follow up, please. Yes, we got time. So
Yeah, for what it's worth, yeah, I find that the way people articulate the scaling law essentially is very in many ways, and depending on the way you interpret it, it can actually be a feature in which understanding how the data is being expressed as a representation reading might actually bring you to a different kind of conclusion.
Yeah.
So yeah, that's why I'm like kind of fascinated because I like that there's some kind of pushback.
Yeah, I mean, I think if you look at, to get a little bit more technical, if you look at like convolutional neural networks have a certain, they're a certain bias, like towards locality, right? Because they're doing local convolutions. And that turned out to be a good bias for image analysis. It's important things in images are local for the most part, for the kind of thing they were doing. Transformers have a little bit less bias because, attention is within a sequence is learned. It's not programmed in. And so it's less biased. So that maybe helps in some way, but also it may make it much harder for these systems, requires so much more data for these systems to learn. So I think it's worth testing both kinds of approaches and see, I don't think there's really been a lot of tests of this kind of thing.
Yeah, and also like reinterpreting some of the evidence because there seems to be many ways to interpret it with flexibility.
Yeah.
Thank you.
Okay.
Sven.
Thanks. That was a great talk.
Thank you.
Really, really cool. So I just had a question about concept art. So I thought you made this really good point about why benchmarks are sort of unsatisfying. Yes. How do we know what they're measuring? We don't. What about data contamination? What about shortcuts? You're just maybe sort of training your AI to sort of like solve these particular problems and sort of like this is like a proxy and not the thing you actually care about. And I wasn't sure why you think that concept art does better than the existing benchmarks. I mean, I guess data contamination, maybe you have to worry less about it if you're keeping the data under.
Yeah.
But the other things I thought, this sort of like shortcut worry, I didn't see why concept art is like not subject to that. And also the worry that, how do we know what this benchmark is actually measuring?
Right. No, I mean, I agree with you that the shortcut issue, I think it does mitigate that somewhat because we look at a group of tasks that are related by concept. And if the system gets 80% of them right, but misses 20% of them, that's saying like, well, it doesn't really get the concept. There might be shortcuts that it's using because it really should get all of them. So, but if a system could solve all these problems, so what? What else could it do? Well, I think, I think this, if you really solved it in a data efficient way, and the way that people are solving these now is they're throwing a ton of compute data at it. But if you solved it in a data efficient way, maybe you would come up with some principles that would be useful for other tasks. I don't know for sure. But I think the benchmark issue is really difficult. And I don't think anyone has the right answer for how people basically, their solution is, well, let's just take all the tests that test people and give them to large language models and see how good they are. And then we don't know what to do with that. Yeah.
Osman?
I have a question. I have a technical question and sort of a sociological follow-up. So the technical question is, so we know that a lot of these systems transform particular to single set processes, And so sometimes if you have sort of multi-step reasoning process, it's particularly difficult to answer the question. Yeah. But if you cascade them in particular ways, you can get them to solve questions that they were not able to solve in the first place. And so there's a question here about whether it might just have to, some of this behaviors here might have to do with performance constraints, like the sort of and whether or not maybe the thing you should be doing right now is that trying to, so people are talking about sort of these agentic meshes now. So I want, so this is a technical question. I want you to think about get them to do more.
Yeah. Okay, so there were sort of two questions in there.
No, that's the first question.
Okay, wait, let me make sure I understand what you're asking. So you're asking about performance versus confidence,
Right.
and but I also thought you asked about agent, kind of agent-based.
Right, as a solution, as a sort of technical solution to that. So that physical, right? Whether you can sort of put these systems together in particular ways that will become these.
Oh.
Actually, sort of force what competencies might be able to actually.
Okay, can I answer that one before you get to the next one? Okay, so performance versus confidence is, yeah, so that's becoming something people are starting to talk about in large language models, and they're saying things like, maybe, I think one example was you ask the system, you give system two sentences and you ask like about the grammaticality in two different ways. You say something like, are these, which one of these is grammatical and which one is not? Or you just look at the log likelihoods of each sentence. It's sort of in the probability distribution of the model. And it's much better using the latter than the former. And the conclusion was that the former puts on a sort of performance or task requirement that the second one doesn't do. And so it has the capability of grammatical judgment, but it can't do the performance part of that. I'm not sure that, you know, how far you can take that. And how much kind of internal probing you have to do of the system. And I know that people who talk about performance competence in humans, it's a kind of muddled discussion, it's a muddled topic, what those things mean. So I don't know, I've been thinking about this, and I've been thinking about trying to write something about this, but I still feel kind of confused about the whole topic, but it's an interesting topic. As for the agent thing, where you're sort of having sort of a collective intelligence of these systems. Yeah, I find that really interesting. And I actually have working with a postdoc who's looking at some of that stuff, whether they can sort of help each other and communicate in ways that will be useful as a collective. So
and I'm asking the social worker.
Yeah.
So I'm going to channel tech for a little bit here, and it's going to be that way. So one of the sort of things that people, so one of the ways you can sort of think about some of these understanding failures is that there's sort of an infrastructure to the world, and our thinking is sort of designed to fit that infrastructure, and AI systems don't carry that infrastructure. So they might be able to use it abstractly, but it's in a sort of different abstract space. Now, the tech pro might say, well, the problem here is we should just change the one infrastructure. It's not built for roads for this built for self-driving cars. And I'm wondering whether that is sort of you know, there are like two ways that you want flushing for the two ways so you can put it like a self-flushing for stuff, or you can have them come over to your using some of them. And so tech pro might say maybe what we should do is not sort of try to not try to necessarily solve some of these problems, but you might, for instance, legislate people should avoid shared tools of some humans. So I'm wondering what you might say about this sort of sociological approach to this solving the problem of understanding, which is just impose it.
Yeah. I mean, we already do that to some extent because, you know, we've sort of adapted to, say, Google search, and we know how to optimize our queries to some extent. And people, you know, are now paid a lot of money to do prompt engineering, which is a kind of version of that. But I think it'd be hard to rejigger the world to fit all the, you know, the things that might come up with these big AI systems. But I do think there will be some rejiggering, like you propose, and some of the problems might get semi-solved. Like, you know, there's a lot of there's all these sort of adversarial attacks on these systems, and jailbreaking attacks and prompt injection attacks and what have you, and they're not robust in a lot of ways. And so one way to deal with that is to just make that illegal and with a lot of punishment for doing that kind of thing. And that may be what happens, I don't know. But if you're trying to think about sort of their understanding or their intelligence in a more general way, then it's important to sort of say, to be able to characterize what their intelligence is. And that's kind of what I'm more interested in doing.
So to ask you about how the AI models fail on concept. So you were saying that they don't get the humanlike integration of those cases. Now, do they fail because they learn different rules from the or do they fail almost randomly?
Yeah, that's a good question. So I don't know if you heard that up here. The question was, how do they fail? How do like humans fail and how do machines fail? The machines fail. And we did actually looked at that, and the way that humans were failing was much more interpretable. Either they were just making some careless mistake, because you know they had to actually generate using a editor, an image editor, the grid, and they would often make careless mistakes that we could understand. The machines would generate grids that or descriptions that made no sense to us. So it's maybe, you know, maybe they are coming up with a new rule, but it's not one that we understood.
Being most
Yeah, I didn't look at that.
Debbie.
Thank you so much. So, I mean, I'm kind of stranger to philosophy and AI generally, so I'm coming at this from a history and philosophy science perspective. And I mean, the question is just what is understanding and scientific understanding is the next question, you know, from humans and science. Just wanted to kind of maybe quantify your thoughts about what in some sense is the upshot of asking this very global and general question about can AI understand the world, and why not just take a more piece-wise approach and say, oh, here's a class of tasks which AI right now are measuring than humans are. There are certain classes of tasks AI is not good or some of them. That's about it. This kind of additional question about can AI understand the world? What does it add to?
Well, you know, humans, I think, have a drive to understand the world. Yeah, little kids are always trying to understand things, and they want to understand. They're asking why questions, and they're trying to understand causes, and that's a big part of our intelligence, I think, is that we want to understand, and we do try and understand in this particular kind of way that enables explanations of a certain kind, that enables reasoning of a certain kind, predictions of a certain kind. And I think we want to get machines to do at least some of that. And, or at least that's an interesting area of machine learning, at least that I think is useful, rather than just statistical machine learning. So that's my interest in it, whether it makes sense to use such a global sort of fuzzy concept as understand. Maybe understand needs to be re-engineered to actually be more meaningful. And in fact, we had a little workshop on understanding at Santa Fe Institute, and David Chalmers, who I'm sure you all know of, gave this talk where he listed like 20 different kinds of understanding. P understanding, E understanding. And maybe that's what we have to do. You know, these terms are, you know, I remember Marvin Minsky talked about these mental terms like intelligence and consciousness and understanding. We called them suitcase words because they were like suitcases that were packed with different meanings. And we had to open the suitcase and pull out all the different meanings and make kind of taxonomy of them. So I'm down with that.
Ready? You must speak up.
Yeah.
My question is general approach. So I'm thinking of like one judge and understand. But now, that's always people are still sticking to that, I think, especially out of the reason that, like, kind of execute not, and only, and now, I'm just not really sure why now is the time.
Yeah, so the question was, so with AI systems, we can actually like somehow look out under the hood more and see how they're doing what they do. And I think that, you know, there's a lot of people trying to do that, obviously. There's this whole subfield called mechanistic interpretability in AI, where people are actually trying to come up with what are the mechanisms underlying the system's capabilities. And, you know, we saw that with the Othello GPT, where people were looking at the internal activations of the network and trying to use a classifier. People actually do that with neuroscience too, to try and do the same kind of thing. But I don't think people have yet developed the right tools, or maybe even the right conceptual vocabulary for understanding these incredibly complex systems that we have built with trillions of parameters and, you know, trained on huge amounts of data. But so that's why people are using performance-based measures, just because it's still very hard, even impossible right now, to figure out how to describe what they're doing on the inside, like just like us. So, but I think that will, you know, people will make progress on that. And then maybe we'll be able to say in a more kind of rigorous way why they can do what they do, and to predict better where they're going to perform well and where they're not. So, yeah.
Yes. Thank you. Yeah, thanks for the talk. I really like the work on like teasing out abstract reasoning. One worry I always have with that on the like letter or number-based tasks is like the LLM won't see letters, right? The LLM it gets represented tokens, and tokens might look weird. Like for example, one thing that might happen might be that bracket A is represented as one token to the LLM, and then there's the space as a token, then there's the other bracket as another token, or something like that. And this will be very context dependent, depending on whether there's a backslash before that. This will look different to the LLM. So I always have like this worry that what the LLM actually sees to it looks very different than like how we perceive the task as it is presented in text. Is that like, is there a way to make sure that that is not a problem?
Yeah, well, I mean, one of the things that we do for each of these tasks is to first make sure that it has a grasp of the task itself by asking it, you know, what are the letters in this? And it's able to do those kinds of very simple answers about simple questions about what elements the task involves. So I don't think there's a problem of tokenization or anything there. It definitely knows what letters it's dealing with or what numbers it's dealing with.
And these are in the same prompt, like the making sure task and the.
Yeah, the
Okay.
separate prompt,
Okay.
separate test. Yeah, we don't do it in the same prompt. No,
Okay, thank you.
it might make a difference if we did. I don't know. We didn't try that.
Please. Another question, right? You? Yes.
So the question regarding, so we talk about the benchmarks and how we evaluate. Possible to train things. For example, I also mentioned this. Validity of want to say a word about the details, but I think that we kind of wrapped it out. It's basically pre-trained GPT-4o, which is don't have the slots. But they do that training, post-training, like asking, especially the math and the planning question, which they do have verified, which can tell, we generate, if you do the problem like 100 times, you know which one's the next one. And then they just let the model generate that, and then do the selection, and then create kind of training back and make the model bigger. So I think maybe this two community, which I think there was a previous question on the scaling. Now they call it test time scaling. This is not a scaling, but kind of like the scaling community and this concept where more of it want to have some structure with, in the models. This community might not completely help each other. Maybe what was understand in the second community could be maybe put it into the training data with training procedure and make it better. Like we keep working on that. Is it possible to turn whatever we're talking about today about this like validation and understanding into what could be maybe a training procedure or interactive procedure or knowledge building procedure or even the data to make it do that. Just a background on we are working, like where my group is working on AI stuff, so that's the perspective as trying to get maybe the other communities knowledge can help us to do better training process in the data task beyond the curve.
Okay. So the question was, you know, can we do training better to be able to deal with some of the problems I talked about? And yeah, it's certainly possible. I mean, yeah, a lot of people were trying to do that, obviously. And as in the talk yesterday, OpenAI is focusing that for some of these reasoning talks on training the system on, you know, reasoning traces that either people or other, you know, GPT-4o has generated, and then training some kind of reinforcement learning model to figure out how to search this giant tree of possible reasoning traces to navigate it. So yeah, I mean, that's a very big open question, how to do training better rather than just scaling up on everything you could possibly suck into the model. You know, if you look at, there's a bunch of people in developmental psychology who are now thinking about how they can take the insights they've learned from how babies learn and make AI more efficient and more robust. For instance, with what's being called curriculum learning, where you actually learn, you don't learn just indiscriminately on everything, but you learn certain things first, and that helps you learn more robustly on other things next and figure out the right curriculum. So yeah, I don't know the answer, but I think there's a lot of interesting approaches to that.
Thank you so much. That was wonderful talk. I've been really excitedly told for a while. I am wondering how you would best be able to test the modal and or causal structure of concepts. And it strikes me that there's a sort of genre of ways of thinking about tests for this, including sort of loose philosophical interpretations of how to test for something like competence in the frame problem, which kind of frame problem, in which like Dennett has responded to the frame problem, and then things like the coffee making problem, and these are designed to test causal or modal structure of understanding. And I wonder if this sort of test that is kind of like an IQ test that is text based and so on really gets at that. And I'm wondering if you can say more about how this gets at that. Yeah.
No, I don't think it fully gets to it. And I think we do need new sort of test arenas, if you will. One thing that I've been looking at lately is how comparative psychologists test animals. There's a lot of work on testing, say, chimps for their causal understanding. And they've come up with all kinds of really clever experiments that are really hard to carry out, but they've done them that show that, especially if you do it in an ecologically sort of thoughtful way, that these primates have quite subtle causal understanding of things, especially social behavior. And I think that you have, AI people should be inspired by that kind of work in very careful, controlled experiments of the kind that people in comparative psych and in developmental psych have done. I think it's been inspiring to me. And I think, more collaborations along those lines is going to be a very good thing.
Just my power as a chair to follow up on
What?
that. I will take my power as a chair to follow up on that question. I mean, I do worry you have exactly the same kind of questions you've been asking about AI in those two fields. I mean, if you know a bit about developmental psychology, you have on the one hand the Spelke and Carey of the world that postulates that behavior of babies and toddlers is driven by more or less conceptual representations of the world. And you have on the other side the Linda Smith of the world that says actually not at all. If you look at developmental psychology, at comparative psychology, you have for one Tomasello, you have one Povinelli, who just says actually it's all heuristics. So, I'm not quite sure we're going to be learning that much by looking at fields where the same debate has been played again and again and again with the same stalemate, as a matter of fact. I mean, I don't want to be pessimistic, but
they can shake each other up.
that would be the optimistic outcome, I suspect.
Yeah, no, but these are hard questions, right?
Yeah, exactly. Yeah.
And I think, they come up in interesting ways in different disciplines. And so it's worth looking at them. Yeah.
Please. Yeah.
Yeah, I think my question is related. I mean, when I read understanding the words in the human language, I think part of that is understanding all the humans.
Yeah.
And I'm curious. I mean, this is my first question. The other question is still related to that sentence. It's like, I mean, I'm not convinced that AI can develop a theory of my mind because it doesn't have its own mind. And how could it ever develop a mind
And because the way we develop fear of other people's minds is using, part is our self-knowledge. How can it ever have like, self-knowledge about itself to project? So that's my first step. The second question is about this idea of like mental models, because we don't all develop mental models in similar ways. So in different cultures, people organize knowledge in very different ways. And when I see those types of tasks, I mean, obviously for someone who grew up in, the US or like, so whatever they call, Weird.
Yeah, exactly.
So, I mean, if those people grew up, sort of like seeing those type of tasks.
Yeah.
But if you go to a completely different culture, who would, have no idea what does that mean,
Yeah.
right? So like, I don't think I can convince myself that it's developing a world model, because there are like hundreds, thousands, millions of world models out there. I just want like, what are your like thinking, or how are you thinking about this idea of like multiplicity of ways of understanding the world, of structuring the world?
Yeah, I mean, for the first thing, you were wondering how a machine could sort of have a conception of itself. I think I don't see any reason why it's not possible. Self is a concept, and we could give these systems the ability to reflect on their own thinking and some kind of metacognitive abilities.
What about feelings? What about empathy?
Yeah.
Yeah, and
They're difficult questions, and they've been questions in AI forever, right? The second question about different world models is like, yes, different cultures have different ways of thinking about the world, but I think there's a lot of just commonalities, because we all experience the physical world in similar ways. So I think, there's going to be, and languages, different languages, while they can be quite different in the way they organize concepts, they all can be translated. They all have more or less the same kinds of concepts behind the words. There's some exceptions, but I think generally we're all human, and so we all have the same kind of bodies, we all have the same kind of brains. There is a lot of commonality there. But yeah, I mean, the cultural issues of evaluation do come up, obviously, in this kind of field.
Yeah, please.
Yeah, so as scientists, I mean, it's very attractive for us to look for principle, understand it. But I think what's happened with these large language models, it's sort of turned things on its head. So we can be more humble and learn something from this. So for example, the concept that just predicting the next word, the next letter, would give so much power, I think was a shock to everybody. And in fact, it really debunked very principled ideas like Chomsky or Fodor or others, actually. So I think there's a way of turning these things on their head and looking at it and seeing what it's challenging us in terms of, so for example, one of the examples you gave earlier was dismissed, well, it was just a bunch of heuristics. Maybe that's what we're doing, a bunch of heuristics also. So so it's similar to what you're saying. So I think there are two ways to look at this, and to discuss what this last person talked about. I do believe actually one can develop very principled models for world models and consciousness. For example, I work on consciousness, and we are looking at underlying principles. So I am a principled person, but I have to be very humble and say, wow, I didn't know these large language models could do so much. I would never have predicted that, ever.
Absolutely. And I think there's extreme positions on both sides, though. There's people who say it's a stochastic parrot, it doesn't think, it's clear, it has no ability to reason. And there's the other people who say, we're 2 days away from AGI. So I think we're all trying to figure out where we should be on that spectrum.
It's also early days. I mean, this is 3 years.
Yeah.
My gosh.
David.
what's the match like between how well the LLMs do on the benchmarking test and how well they do if they're asked to explain their answers?
How well did, so,
You know, I give it one of these questions, it answers it, and
yeah,
does it systematically give a sensible explanation as to why that's the right answer?
no. I would say that sometimes, but not reliably. And I think people have actually studied this more systematically than I have, which is to say they've looked at this sort of chain of thought kind of prompting, and when it actually does go through the steps of its reasoning, they ask sort of how faithful is that to what she did. And there's a lot of cases where it's not faithful. And that if you, there's one paper that I thought was amazing, where they said, let's think dot by dot, where they just had it print out dots instead of words. And it helped it quite a bit. Because it was, I don't know, giving it more computation time. I don't know exactly why it kind of worked. But yeah, I think that there's still a lot of research to be done on that very question. Yeah.
Please.
Thank you so much for this. I'm really interested in social implementation and also your thoughts on your own use of AI and LLMs like in your everyday life. So first of all, do you use them? Do you find them useful? And then second of all, are there places where you think that we should not be using them? I'm struck in particular when your comment about, you don't need a nuclear reactor to power a child, that there's spaces where we've kind of ethically carved out, not here. And those spaces are very jagged too, socially. Yeah. So I'm curious on your thoughts on that.
Oh my God, that's such a hard question. I mean, yeah, I use them. I use them to help with coding. They're fantastic. I use them to help with like formatting stuff and, making tables and LaTeX and all of that. The really kind of mundane things. I haven't really used them to help writing at all. I hate their writing style. And I haven't used them to help thinking. I know other people do. And some people find them really useful for that, just to brainstorm, have a conversation with them and brainstorm. Where shouldn't we use them? That's such a hard question. Yeah, I mean, everybody's struggling with that. Should we use them to create art? Should we use them should students use them to do their homework? I mean, should professors use them to grade papers? I don't know. I find it really hard.
Here's an idea.
And I don't know. I think that's, yeah, I find that really, I don't know if I have a good answer for any of that.
Please, yes.
So thank you, that was a great talk. So my question is that a lot of these models suffer from these long tail probabilities, like that self-driving car you showed, that stop near the stop sign.
Yeah.
It's sort of these rare events which will probably never occur on a normal driving. My question is that what if these kinds of rare events, like the data, which is total number of patterns which you can generate, is much more than what we can reasonably generate, even if we have sort of infinite amount of data.
Yeah, I mean, the world is long-tailed, right? Stuff happens.
Yeah.
And even though you aren't likely to encounter it on your drive, if you have a billion cars out there, somebody's going to encounter it.
Yeah.
And that's true for everything that people do. And so I think that's a big problem in all these systems, and that's why somebody proposed, like, why don't we should engineer our world to allow them to be robust. Right. I think that is what's going to happen. But there's still the long tail is very long, so weird stuff is going to happen, and they're going to, humans right now at least seem to be better at dealing with these,
right, very
improbable events than machines, which is why you have people stepping in, like Waymo, to teleoperate the cars if they get into trouble. People know what to do. Yeah.
This makes me feel that data is not the answer. Data is not the complete part of the answer, because how do you deal with such very rare events which humans are good at managing, but these models completely fail? It just seems to be intuitively that maybe data is not the complete answer to the question.
Yeah, I agree. What is the complete answer? I'm not sure. You know, we have something called sort of common sense that we use, and it involves a lot of different processes. And maybe analogy is going to be.
And for, yeah, please.
Just as a body. Say, you achieve. To me,
Well, I have an alternative solution besides embodiment.
Yeah.
Okay, so.
Is there another way to go about this problem?
You know, it's possible that just by learning more and more data, that language is, you know, a lot more expressive than we, I suspected that the systems have learned a lot about the world just through language. Yeah, they learned a ton about the world. But, you know, they have gaps, for sure. Maybe, you know, scaling up more and more. I mean, I don't think it will, but it's possible. I don't think it's, you know, there might be more than one way to get to it. So it's just a lot more inefficient. I don't know. I think it's possible, but I think it's going to end up being sort of impractical. There's not enough data, and it's expensive to get data. It's you know, involves stealing copyrighted materials and all of that stuff. So I think it would be a much more efficient way. There are more efficient ways to do it, but we're still trying to figure out what they are.
Go ahead.
Quick comment on this point that for the kinds of examples you were giving the AI model for opinion, it's not at all clear to me how adding embodiment or don't seem like that.
How do you think that we do it? Why don't we fail?
It's not, it doesn't seem to me that it's active squares that are good way to generalize it.
Have an understanding of the underlying concept. Side.
Sure. Yeah. So I'm okay with the idea that there might be some concepts. I think those concepts are then studied. And this is just a take on it. I feel like there's an unarguable premise about whether those concepts.
Yeah, I can't prove that that's how people get those concepts, but you know, that's one thought that maybe very young, you're doing all kinds of experiments that use your body and map on spatial semantic concepts to things that you can do with your body, that helps you understand those concepts.
We are done. Thank you very much. When we invite you, we have a reception on the 11th floor. So that's the 10th floor. The next floor, that's the steps. And please join us for the reception. A small gift for you.